Thanks, Dr. Pierre. And good morning, good afternoon, everyone. Today I want to talk about polymer-based deformable lens for shoulder tracking. Starting with a brief introduction of my project. Nowadays, a large amount of solar panels are used for absorb and convert sunlight to electricity, but it comes with a high cost because large area are used. So in order to lower the cost, the solar concentrator are used to focusing the sunlight to a small area of a solar cell. But the problem is as the sun is moving all day, so the solar cell at a specific area can only absorb enough intensity of sunlight at the specific area. So if we add a motor system to move the solar cell according to the movement of the sun, it also adds a cost. So if we use a low-cost polymer and apply the heat at a specific area and generate lens according to the as the sun is moving, so the solar cell can absorb enough intensity sunlight all day. So how to do it? And applying heat from the bottom of polymer, the density of the density of the polymer on the bottom was lower. So because of buoyancy, the lower density polymer were going up, and the top layer of polymer, because it will keep the horizontal surface, so it was going down, so it caused convection. And when the higher temperature polymer going up, because it will fight with the polymer on the surface. So the surface tension play an important role on the fight. So at the liquid air interface, the water molecules on the surface will have more attraction. So the net effect is that in water force attract the water molecules inside to form a water bead. So for example, like the water strider, he uses the surface tension to walk on the surface of the water, so its feet can cause the indentation on the surface. So it increases the surface area, and because heating from the bottom of the center, so as the surface tension is a function of temperature. When increasing the temperature, the surface tension is decreased. So the molecules in the center with a weaker surface tension is pulled by the molecules on the side with a stronger surface tension. So it causes two bump on the center. Applying this idea with a smooth surface of polymer, we can achieve this polymer lens. So the polymer I choose is polystyrene because it's when it's heated, it's always amorphous. If the polymer is semi-crystalline, it will cause the stress problem. When I applied this polymer on the surface of this glass substrate, the stress problem will crack the glass, and also it has a low glass transition temperature. Because I use the polymer bead, so I needed to find a solvent to dissolve my polymer. I choose toluene because it's very easy to dissolve the polystyrene, and this is the start mass ratio I'm using to mix the polymer and the solvent, and this is the final ratio I used for my heating experiment. We can see that the ratio is changed a lot because the vapor pressure of the toluene is so high. So we need the toluene to stay in the polymer because it will lower the viscosity of the polymer. So when it's heated, it can flow easily. And we choose ITO as the heating source because its electrical conductivity is high. So when you apply heat through the ITO, it can generate heat more easily. When you apply the current, it can generate heat more easily, and it's optical transparent, so it allows sunlight to travel through and reach the solar cell. So and it's also easily etched by HCl. So applying this idea to a low melting point polymer, we can achieve the polymer lens. So I measured the temperature of my ITO at a different level of heating power. We can see that when increase the heating power, the temperature increase and decrease from the center to the side because the heat dissipation. So starting with my experiment, I cast the polymer on the surface of this ITO stress with a 6 millimeter width ITO, and put it in a glass sealed chamber. So the chamber is filled with a nitrogen atmosphere. The atmosphere can prevent the polymer from oxidation. Then applying an incident light from the light source on the top, it travels through the polymer and illuminate on the axis screen on the bottom to determine the focal properties of my polymer lens. I use a web camera to record these results. So from these pictures, we can see at higher voltage, we can see the focusing line is sharper. And when it's 9 volts, it gives us different view. So there are 2 focusing lines because there are 2 bumpers. And I measured the surface profile of this polymer lens at different heating power. And when increase the heating power, the lens radius is decreased, so the focusing line is sharper at higher heating power. And with the same profile, just at different scales, we can determine the focal length. And by the data we got, so applying all the data we got into this equation. In this equation, this object distance is the distance between the source, the light source, to the lens, and the image distance is the lens to the axis screen. So in my experiment, the object distance is 44 centimeters, and the focal length is we determined from last slide is 6 centimeters. So the theoretical image distance is 6.95. And in my experiment, I observed the sharp line when the distance is 7.5 centimeters. It kind of fit well. So then I use the optics lab, a modeling software I can use for the optics design and analysis. You can see when the light emitted from the source reach the lens, and it will focus in 2 lines. So and also at 9 volts of heating power, we can see the convection. I mentioned before the Rayleigh-Bénard convection well. Yes, and these 2 focusing lines will flow further. So in conclusion, this polymer-based lens can be achieved, and surface tension play an important role on the surface fight. The focal length decreased with increase in heating power, and also the distance between 2 lines are increased. So in the future work, as I mentioned before, we need to find a more suitable polymer solvent for my material device, and I will try to make this polymer lens into the real application. So here I want to ask my supervisor, Dr. Adrian Kitai, for his idea and kind help. Also, I want to thank the Dr. Wakafas and Dr. Johari for this idea of this convection and flow effect, and Dr. Brook for his suggestion of polystyrene. So thanks for your attention. Thanks.